Hello, everybody, and today we're doing the pre-lab lecture for the Exploring Glassware experiment. So first, let's get into the different types of glassware that you would normally see in a chemistry lab. Normally, these are all up on the shelves for you to see, but since we're virtual, we'll just have to look at some pictures. Okay, so we've got the beaker, the graduated cylinder, the Erlenmeyer flask, the burette, the volumetric pipette, and the volumetric flask. All these look a little bit different. They all have different uses, and that's kind of the entire point of the experiment we're doing today, is figure out what they're used for, how good at doing that thing they are, and how they compare to each other. So the first thing to look at is whether they are to contain or to deliver pieces of glassware. To contain are specifically made to hold a certain amount of solution. So the beaker, the graduated cylinder, the Erlenmeyer flask, the filtration flask, and the volumetric flask. A filtration flask just looks like an Erlenmeyer flask with a little side arm that you would use for vacuum filtration. We'll actually use one later in the semester. But all of these are to contain pieces of glassware. The increments that they're marked off for are to hold that volume. To deliver are specifically intended to transfer a certain amount of solution. Graduated cylinder, the burette, and the volumetric pipette fall into this category. You'll notice the graduated cylinder falls into both categories. That happens. Sometimes the graduated cylinder is specified one way or the other, depending on how it's made, how the increments are marked off on it, but it can usually straddle both groups and be used for lots of different things. Next thing, since we're talking about glassware and putting liquids in them, we need to be able to record volume measurements correctly from these pieces of glassware. There are two major pieces you need to know. First, you need to be at eye level of the point you're trying to record. And the point that you're trying to record is called the meniscus. Water, any of the solutions we'll be using, most liquids will actually bend down slightly. You'll see the edges curve up like you do in this bottom right picture. You get this bowed shape. That's called the meniscus. And you want to read your volume from the bottom of that meniscus. And again, you want to be at eye level. So if you look at the left picture over here, if you're above it looking down, your meniscus will look higher than it actually is. If you're beneath it looking up, your meniscus will look lower than it actually is. So if you're right at eye level, meaning you might need to squat or kneel down or something to really get that measurement, that's what you have to do to get an accurate measurement from whatever glassware you're using. The next thing is to record the right numbers for your volume. And this is where significant figures will come into play, and I'll get into that in just a minute. This is a picture of a burette. So it's a little weird. Some of the pieces of glassware we would use they're numbered backwards, so 0's up at the top and whatever they go to, in this case 50, is down at the bottom. It doesn't really change how we read it though. The next thing to do is figure out where we're measuring from. So our meniscus is down there, kind of where that 5 is, and that's the point we're going to be looking at. Now let's see if I can draw on here. We need to figure out what each of these increments values are. So we see the 4 and the 5 that are nicely numbered for us, but then there's 10 marks between 4 and 5. So that means each of those is 0.1 milliliters. So we have 4, 4.1, 4.2, 4.3, 4.4, 4.5, and so on. So our meniscus is between this increment, which is 4.8, and this increment right here, which is 4.9. There's no more marks between that for us to really know what number it's between. So we have to estimate, we have to guess. And in this case, we could guess maybe 4.86, 4.82. It'll look different to different people slightly, but it's somewhere around 4.85, 4.86, probably somewhere in there. So that would be the volume we write down. Now, the number of decimal points you write down for that volume is limited by your glassware. So we just said this would be 4.86. It would have 2 decimal points. That means any volume we took from this needs to have 2 decimal points. So for example, if it was right on the 4.8 line, it still needs 2 decimal points and it would be 4.80. If If it was exactly on the 5 mark, it would be 5 with 2 decimal points, so 5.00. And those decimal points are important. Those will set up our significant figures that we'll be talking about in just a minute. So again, at eye level, from your meniscus, you should be estimating 1 decimal place further than what's marked off. So because this is marked off to 0.1 increments, you need to estimate to 0.01 or to 2 decimal places. And so we could just write that as 4.86, and the way scientists read that is 4.86 plus or minus 0.01. So there is some error in that last digit because you estimated it, and that error is the basis of significant figures. So what are significant figures? Well, they're numbers that count from your measurements. And significant figures are any number that is not a placeholder. I'll get into what that means. But the greater number of significant figures you have, the better your precision. So, for example, going back to the burette, 4.86 plus or minus 0.01. So we have plus or minus 0.01, that second decimal point is where our error is. If the burette was only marked off at 4, 5, 6, we could only estimate to that first decimal point. So we have plus or minus 0.1 error. If it was marked off even less than that, and maybe our estimated digit is the 4, that means 4 plus or minus 1. And so you can see with just the error each time, the error is getting bigger and bigger as your number of decimal points and your number of significant figures goes down. So the rules for what counts as a significant figure. The first thing is any non-zero digit is significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Significant, always counts. Then we have to look at the different types of zeros, because that's where sig figs get messy. Leading zeros, any zeros before your first non-zero digit, are never significant. They are only placeholders. I've got some examples of all of these. Interior or sandwich zeros are zeros between 2 non-zero digits. Those always count. Those are always significant. Non-zero digits we talked about. Trailing zeros is, again, where things get messy. Anything after your last non-zero digit is a trailing zero. It's the opposite of leading zeros. However, their rules are if there is a decimal point, those trailing zeros are significant. There is not a decimal point, the trailing zeros are not significant. It does not matter whether those zeros come before or after the decimal point. If there's a decimal point, those trailing zeros are significant. So let's go through some examples of that. 4.877 grams, really easy. 4877, all of those are non-zero digits. They all count. We have 4 sig figs. 0.004 milliliters. 4 counts, it's not at 0. Those first 3 are leading zeros, which never count, period. Even though there's a decimal point, even though some are after the decimal point, doesn't matter. They are leading zeros that don't count. So we only have 1 sig fig. 5600.044 milliliters. 5644, all of those definitely count. Now we've got to look at our zeros. Those zeros are all between non-zero digits. So even though there's a bunch of them, all 3 of those count, and we end up with 7 significant figures. Just like if it was 5604, you would have 1 in between, that one would still count. All of those are between non-zero digits, so all of them are interior zeros. 0.0092 kilograms looks a lot like letter B up above. Those first zeros are leading zeros, so they won't count. The 9 and the 2 counts, and we have 2 sig figs. E looks very similar, but now there's a 0 at the end. So the 9 counts, the 2 counts. The first zeros don't count, they're leading zeros. That 0 at the end, it's a trailing 0, so it might count if there's a decimal point. There is a decimal point, so it does count, and we have 3 significant figures. Last one, 4510 grams. 451, all of those count. We've got a 0, things get a little messy. It is a trailing 0, because it's after our last non-zero digit. So it counts if there's a decimal point. There is no decimal point, so we're only left with 3 significant figures. I know this can be a little confusing if it's the first time you dealt with it. There are lots of examples and practice online that you can look at. You can always reach out to me to get some help with those as well. I've got lots of practice with determining and using significant figures. So sometimes with significant figures, we might have something or need to write something in what's called scientific notation. Scientific notation has 2 parts. The first part is the decimal part, which will always be a number from between 1 and 9. And then the exponential part, times 10 to some number. That number tells you how the decimal point was moved. The easiest way, in my opinion, to write a number in scientific notation is go from normal, where it's all written out, to scientific notation. So move the decimal point if there's one shown. If not, you should know where it is. It's at the end of that number. And you're going to move that decimal point until you get a number between 1 and 9. Then the number of times you move that decimal point is the exponent for your 10, where it's 10 to the n. That n is the number of times you moved your decimal point. The last thing is whether that number is positive or negative. If you're going from normal to scientific notation, if you moved the decimal point to the left, then that number is positive. If you moved it to the right, that number will be negative. Got some examples. So 635000. There's a decimal point right here, even though it's not shown. We're going to take it and move it 1, 2, 3, 4, 5 times, because this would be 6.35, which is between 1 and 9. So that's how we know to stop. Before that would have been 63, 635. We go after that. It's 0.6, which is less than 1. So this is where we stop for our scientific notation. Now, our number in scientific notation needs to have the same number of significant figures as the number we used. So now already sig figs are coming back. So our first number, 635, those 3 count. 0, 0, 0, those are trailing zeros. There's no decimal point, so they are not significant. So we had 3 sig figs. We need to end with 3 sig figs. So our number 6.35 times 10, we moved it 5 times, and it's a positive because we moved it to the left. So 6.35 times 10 to the 5th. If we look at the next one, we have the decimal point. We're going to move it to the right 1, 2, 3 times. So 6.35 again. Check our sig figs. These are leading zeros. They don't count. 635, 3 sig figs. Our answer needs to have 3 sig figs, and it will. We moved that decimal point 3 times, and since we moved it to the right, it is a negative 3. So these numbers look very similar now. 6.35 times 10 to some number. But the original numbers look very, very different. That's where scientific notation and knowing how to read it comes in handy. Again, if you're struggling with scientific notation, let me know. There's lots of practice online. I have lots of ways to help. Okay. Calculations with significant figures. Again, significant figures are going to keep coming up throughout this course. There are 2 rules when you're doing calculations with them. If you're doing addition and subtraction, you care about the number of decimal places. If you're doing multiplication and division, you care about the number of significant figures. Why this matters is going all the way back to measuring volume. We estimated that last digit, so there's some error there. Well, that error compounds with every other value we use it with. Every time we calculate something, the error in all of those measurements comes together to form the error in that new number. And that's where sig figs come into play. So if we're doing addition and subtraction, we care about the fewest number of decimal places, or the least accurate decimal place. If it has more decimal points than that, then we'll need to round it to truncate it at the right spot. So just like normal rounding, if the next digit is 4 or less, it'll round down. You'll keep the number as is. If it's 5 or up, or 5 or greater, you'll round up. Multiplication, division, you care about the lowest number of significant figures, not of decimal places. And again, you'll round if you need to. So here's some examples of calculations. 0.066 milliliters plus 3.44 milliliters. Especially if you're doing addition and subtraction starting out, I recommend writing them vertically. It's really easy to see where these numbers stop. So mathematically, we get 3.506 milliliters. But based off of our significant figures, we may have to change this number. Our first number has 3 decimal points. Even though it's only 2 significant figures, it's 3 decimal places. And we care about decimal places because we're doing addition and subtraction. Our second number has 2 decimal places. Even though it has 3 significant figures, we care about the number of decimal places. So our second number has the lowest number of decimal points, 2. So we need to round our answer to 2 decimal points. So the 0.50 are our 2 decimal points. We need to round based on the 6, which will round up to 3.51 milliliters. Now, if we're doing division, 15.366 grams divided by 10.5 milliliters. For division and multiplication, we care about the lowest number of significant figures. So our first number has 5 significant figures, 1, 5, 3, 6, 6. Our second number, 1, 5. That 0 is an interior or sandwich 0 between non-zero digits, so it also counts. So we have 3 sig figs there. We do the division, where our answer needs to have 3 significant figures. So we'll get 1.46. 1, 4, 6, those are our 3 significant figures. Make sure you include units. The grams per milliliter is very important, and I'll show you some examples later of why those units matter. This is also an example of the density equation. We'll be getting into density a whole lot more next week, but anytime you've got grams divided by milliliters, you're dealing with density. So here's why units matter. 72.1 grams plus 0.0055 milligrams. So first and foremost, if those units are different, you cannot add them together. To add or subtract, they must be the same unit. So we need to convert them to the same unit, and this is where dimensional analysis comes in. So you can convert either the grams to milligrams or the milligrams to grams. I prefer going grams to milligrams in this case. So 72.1 grams, because we want to get rid of grams, and it's currently on top, our conversion factor needs to have grams on the bottom. We're converting grams to milligrams, so milligrams goes on top. The numbers are then based off of our metric prefixes. There are 1,000 milligrams in 1 gram. You will definitely need to know your metric prefixes. If you're struggling with those, again, reach out to me. There's lots of mnemonics, lots of tricks, lots of things I can point you to help with those. So 72.1 times 1,000 divided by 1 gives us 72100 milligrams. That's what the calculator will tell us. We need to check our significant figures. Don't round your significant figures at every step, because then your final answer gets further and further away from what it should be. But keep track of them. Make a note of how many significant figures that number should have, whether it's written with those significant figures or not. So our first number has 721, 3 significant figures. Our next part, the 1,001, is a metric conversion, so it has infinite significant figures. We don't worry about it. We don't count them. So 3 significant figures at the beginning, we need 3 significant figures at the end. In this case, our number does have 3 significant figures, but even if it didn't, we would want to write how many significant figures it should have to keep track later. So 72100 milligrams plus 0.0055 milligrams. We do the math, and we get this really long answer. Our top number has absolutely no decimal places, meaning our answer needs to be rounded to 0 decimal places. So we get this really long answer, and we're going to round it before the decimal point. It's not allowed to have any decimal points. So this will round to 72100 milligrams. Now, this might look a little strange because that was our first number. We added something to it, but the number didn't change. What that means is our error in the first number is bigger than the amount we added to it. And you can think about it this way. If you have $1 and you add $1, you have $2, and that's a big jump. You've got twice as much now. However, if you had $10,000 and add $1, that $1 is not really going to make a whole lot of difference. Same thing here. Our 0.0055 is so small that we don't really see the difference. And that sometimes happens depending on the error of your calculations. Now here's why units matter. Same numbers, still 72.1 grams, but now we're adding 0.0055 kilograms instead of milligrams. Same thing, if we try and add these, they're different units, we need to convert them. I'm going to convert the kilograms to grams. Same thing, we want kilograms to cancel, so it's on top. It needs to go on the bottom to cancel out. We can convert it to grams, which would go on top of our conversion factor. Kilograms will cancel out. We're left with grams as our unit. The numbers, there's 1,000 grams in 1 kilogram. Again, this comes from metric prefixes. So 0.0055 times 1,000 divided by 1 gives us 5.5 grams. Again, make sure you note how many significant figures it should have. This is multiplication and division, so we care about the number of significant figures, not the decimal places. Our original number has 2 significant figures, leading 0, leading 0, leading 0. None of those count. 5, 5. There's our 2 significant figures. The next set of numbers is a conversion factor. It's a metric conversion, so we don't care about the significant figures it has. So our answer should have 2 significant figures, and it does. So now we can take our 72.1 grams plus our 5.5 grams that we just found and get 77.6 grams. We need to round based off of the number of decimal points since we're adding. Top number has 1 decimal point, bottom number has 1 decimal point. Our answer should have 1 decimal point. In this case, it does, and we don't need to round anything. And now in this case, we added something and we do see a change because the error is not bigger than the amount we added. So again, this is why units are very, very important with every number you write. I'll give you guys another density example. Again, we'll talk about it more next week. Density is just grams over milliliters. So if it has a mass of 12.8 grams and displays 4.2 milliliters, density is mass over volume. Here's why we care about it this week, significant figures. If you do the math, you get 3.04 grams per milliliter. We're doing division, so we care about the number of significant figures. Our top number has 1, 2, 8, 3 significant figures. Our bottom number has 4, 2 significant figures. 2 is the smaller number of significant figures, so our answer needs to have 2 significant figures. So 3, the 0 is going to count, so we'll round after that. Hit the 4, so it'll round down to 3.0. And again, after you round, just double check your number, 3.0, the 3 counts. The 0 is now a trailing 0, but there is a decimal point, so it still counts. So we still have our 2 significant figures, but always, always, always double check your significant figures. That is the easiest thing to miss and is what I see students miss a lot of most of the time. So I brought this up way back at the beginning, talking about measuring glassware and that the accuracy and precision of these might be different. So the accuracy is the closeness of a single number to a theoretical or tabulated value. Normally that number is the average of a bunch of data points, or it's a single data point. Precision is the closeness of a set of measured values to each other. So if we look at the targets down here, the green circle is the average, the black dots are the individual data points. So because the average of those data points is the green circle, and that's very close to the bullseye, it is accurate. Because all of the black dots are close together, it is also precise. We'll look at the next one. The average is the green dot, and the green dot's way off center, so it's not accurate anymore. But all of those black dots are still close together, so it is still precise, even though it's not accurate. This third target is very, very hard to happen, but I'll talk about it for sake of being thorough. You have all of these spread out black dots, so we know they're not precise. But if you take the average is pretty close to the center. So you can have the average value be accurate, even if your data is not precise. But again, this is very, very rare. And the last option is neither accurate nor precise. If all of your data points are really spread out like those black dots are, they're not precise. And the average of them is nowhere near the center of the target, so it's not accurate either. So that's accuracy and precision. And again, that's what you'll be looking at in the experiment, is the accuracy and precision of the individual pieces of glassware and comparing them together. So the ways to measure accuracy and precision. Accuracy is usually measured by percent error. Percent error is actual minus theoretical over theoretical. Note that top difference, actual minus theoretical, is in absolute value bars. So your percent error will always be positive. Whatever that difference is, you'll make it positive and then divide it by your theoretical, times 100%. So the lower that percent error is, the closer your actual and theoretical were, more accurate, better number. Precision is usually measured by something called standard deviation. We 100% will not ask you to calculate standard deviation in this class because doing it by hand is a lot of work. You can have computers do it, but it's beyond the scope of what we need to cover for this course. Again, random error or that estimated error. Values measured and calculated will almost never be exactly the same. I could take this pen and put it on a scale in lab and get some value for it. Take it off, put it back on. The exact same pen, the exact same conditions, and the mass would be slightly different. That's due to random error. So don't worry if not all of your numbers are exactly the same every time. If we're, especially in the post-lab questions, if we're ever talking about if there's a significant change between numbers, or if there's a significant difference between this and what you were told, we're qualitatively discussing accuracy in that case, and we'll just use 20% as our threshold. If it is 20% different, then it is significantly different. If it's less than 20% different, it's not. It's basically the same number. The error in that case would make them about the same number. If we're asking you specifically quantitatively about accuracy, we will tell you to calculate the percent error. So you can always look at that for your accuracy and precision. So again, brief overview of what we're doing. What you'll see me do in the video is I'll have all of these different pieces of glassware. We're going to look at the incremental values that are on them to figure out how many decimal points we can record our volumes to. Most glassware has the error associated with it written on it in addition. So you can look at that. We can compare decimal point increments. We can compare the error. We'll fill it between 2 marks, so we have to record an estimated value. And then use all of that to calculate the density of water. Again, if you were in lab doing this, make sure you use the right number of decimal places. Again, it's a very common thing for students to miss, is not using all of the right number of decimal places, and it will mess up all of your calculations. The volumetric and flask and pipette, you'll see in the video, they only have 1 line marked off on them, so we will fill it exactly to that line. But that's it for the pre-lab talk. You'll watch me go through all of this in the experimental video, and then make sure you get all of your lab data and post-lab questions that should be uploaded to your web courses module. And that is it.